So here we are now gonna see basically we have seen till now basically the ores. So what is basically the actual ore? Basically there are rock and it contains a lot of minerals or the metals. Then this is called a rock. But when this rock contains particularly a single type of metal in huge amount, then it is known as ore. And obviously the same way, if we have to extract this ore, like if this is the ore and which is the abundance of a single metal, and if we want to get this metal, we want to extract it, then obviously the ore is not present as alone. There might be some impurities in it in smaller amount. This have to be removed to get that ore. So this impurities that is contained in the ore, the impurities 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 contained in ore is called gangrene. And obviously this is the impurity that is present in the ore that has to be removed. And if we remove this impurities from the metal, then we get the ore from which the metal can be finally extracted. Let's see how different type of reactive elements can be extracted from their ore, and how we remove the impurities that is the gangrene that is present in the ore. Look at the reactivity series. Then first of all there is the lowermost reactive element. Obviously this element can be easily extracted from their impurities by normal heating. Like by heating, these compounds get converted into their oxides, and after forming the oxide the metal can be extracted. Example, if we take, that is the mercury. If mercury is if we heat the mercury, then converted oxide, and we react with the higher reactive element, then the mercury gets released. And if we take the middle reactive element, if we take the middle reactive element like the iron, zinc, lead and copper, usually this have to be converted. Usually these compounds are found usually in sulfide and carbonate. And obviously as we know that this carbonate and sulfide is not easily can be extracted, their metal can be extracted. So this first of all to convert it into oxides. Sulfide and carbonate convert into oxide as easier to extract metal from oxide. So first of all, if we talk about the sulfides, like we take it to the next page. Like if we take the sulfides, then this have to be first converted into oxide. Obviously why we have converted them into oxide? Because it is more easier to get metals from oxide than to sulfide and the carbonate. So first of all they have to be converted in oxide. And how it is done? It is done basically by heating in excess air. And this process is known as heating in excess is known as roasting. And when carbonate is converted into oxide, this is basically done in limited air supply. Basically heating in limited air supply, and this process is obviously known as calcination. Calcination. So what is the roasting? Basically, when excess air is given and the heating is done, it is called as roasting, and when it is limited air, then it's known as a calcination. And after the when we got the oxide, this oxide can be reduced with a suitable reagent, reduce with a suitable agent to get the metal. And what reagent that we use? Basically usually we use the carbon, because as for metal active element, the carbon is used to reduce them to metal stage. And if we now talk about the higher reactive metal, like we take on the next page, we have seen how the sulfide and the carbonate are converted into oxides, and they are with a reducing agent like the carbon, they are reduced to get the metal. So same way, there also we use displacement reactions. So basically displacement reaction, what is there? Basically a metal that is more reactive with B salt, remove the element and form A salt plus B. So basically here more reactive element replaces the less reactive element from a solution. Same way, the more reactive element we use like sodium, magnesium, calcium and aluminium are used for the displacement reaction. And obviously as this reaction is a displacement reaction, this is highly exothermic. These reactions are highly exothermic, and because of which a lot of heat is released, and this much is that sufficient that it can be used to join track or tracked machines. Basically after the carbon part, with the displacement reaction we can be used where a strong more reactive element replaces the less reactive element from its salt solution, and we can use compound like sodium, calcium and aluminium. And obviously this reaction is highly exothermic, and the heat it released in this reaction is so high that can be used to join tracks or cracked machines. Now we on the next page see uh, the finding removing impurities from highly reactive elements. So when we talk about the high reactive elements, probably they are more reactive to oxygen than carbon. So that is why it is not easily it is not possible to remove this compound from the carbon from by using the reducing agent like carbon. So how it is done? Basically this is done by electrolytic reduction. What is electrolytic reduction? So here we draw first of all at the cathode, or we can say the negative end, or the cathode. Here we make the pure element, and here we take anode, positive we know anode. Here the impure element, or the ore that contains the pure element, or the impure sample that contains the pure has pure substance in it. So basically what happened when we pass the electricity from this when we pass the electricity, then this impurity this got dissolved in the solution and form here, that is known as they are formed near the anode. So basically they are known as the anode mud. Basically what is this anode mud? They are the impurities. And the pure metal here present, this pure metal, like if we represent as a star, and this is a star is the pure metal. So this pure metal usually get deposit at the cathode end, the negative end. So basically what will happen, that when we supply electricity here, then obviously this from the impure solution, the impurity dissolve in the solution. We have taken here the electrolytic solution, and the impurity get dissolved in the solution and form here a anode mud. And on the other hand, the pure metal get deposited at the pure element that we have put in the cathode. So basically what happened at cathode, pure metal deposit at pure sample. Anode, anode, impurities dissolve in solution, and pure metal go to cathode. As pure metal go to cathode, and the impure metals, they go dissolve in the form solution and forms anode mud. What is formed by the anode mud? Basically the impurity that dissolve in the solution from the impure sample. So we can summarize is as if the more highly reactive element, they are more reactive to the oxygen, so they can't be reduced with the carbon. So what we use, basically we use the electrolytic reduction, where what we done basically, at the cathode, the negative end, we put the pure element, and the anode end we put the impure element. So when we supply the electricity, the impurities get dissolved and form a anode mud near the anode end, and on the other hand the pure metal got deposited at the cathode end. So basically, cathode, pure metal deposited at the pure sample, anode impurity dissolved in the solution, and pure metal goes to cathode and forms anode mud, that is the impurities. And how it is done? Basically, this is done by passing of current, either representative of current or the electricity having passed through the cell. Then this is electroradiation, where the impurity get dissolved and form the anode mud, and the purities go to the cathode, that is a positive end, and the impurities that remains on the sample, that is basically that impurity get dissolved in the solution and form the anode mud, and the pure element goes to this pure sample, that is at the cathode, that is negative, and anode is the positive end. Positive end we apply the impure sample, and at the cathode we apply the pure sample. So for highly reactive element, as they are more reactive to the oxygen than the carbon, the electron reduction is done, and we see in the process. So if we summarize all of this, then if we say for the impurity that is present in the gauge, and they are physical and chemical properties, and lower metal basically can be reduced by heating and converted to oxide, and obviously we can then the reduction we get the mercury. And whether the middle, that is iron, zinc, and lead and copper, usually sulfides and carbonate can't be easily reduced, so first of all they have to be converted to oxide. And how this is this, basically sulfide oxide, excess air when we done heating, that is no roasting, and when we have limited it, then this is known as calcination, and the reducing agent is the carbon. And sometimes we can use the displacement reaction, at very high heat it is released in the compound, and the element that we use is sodium, calcium, and aluminium. And obviously that high heat is that much that they are probably found in the impure stage, and obviously that is used to join tracks and over the crate machines. So basically, and after that we seen the highly reactive element, and obviously they react with more with oxygen than with the carbon, so we use the electrolytic reduction here. So when we applied anode the impure sample, and cathode the pure sample, then impurities get dissolved and form the anode mud, and the purities go to the cathode. So this way we can separate the impurity with the samples. Thanks for watching. I have told you that the lower reactive element, we basically form the heating, we do the heating that form the oxide, and thereafter the oxide we reduce it when we get the metal. So basically I have told you that metal, that is the mercury. So basically what I have told you, that after that we use a highly reactive element. Obviously this can be done to get the mercury, but usually when we heat it, the oxide, we get the mercury itself. So when we heat it, it's from the oxide, and from it we get easily the mercury itself. So usually this displacement reaction, we can, if for the lower reactive element, can be wasteful in terms of wasteful in economic value, because obviously when we do the economic work, then we have to focus on the money aspect, and on the money aspect it is more like a waste, because when we do the heating, it form the oxide, and from the oxide we can easily get the mercury. So basically doing a displacement reaction is sometimes a waste of time, and same time as well as economically not a good idea to do so. So that is why lower reactive element usually done heating is done, and thereafter is form oxide, and from it we can easily get the metal itself. Usually displacement reaction not required, and economically that can be not that a good idea to do so. So that we have to keep in mind.